All right, so again, this is our chapter 14. We have one more chapter, which is amino acids. And the previous chapter that we've seen, we've actually covered carbohydrates. And as I told you last week, right, these molecules are actually large molecules. And the carbohydrates are actually polymers, and proteins are also polymers, but lipids are not polymers, right? So what was the polymers again? In the polymers, you have the monomers, and then there was see my pen, okay. Change my laptop the other week, and yeah, so there was like a monomers, right? And then if you connected the monomers like that, then you get the polymers, right? And the previous chapter in carbohydrate, we've seen that the monomers was actually, like the simplest sugar. We call them monosaccharides, if you can remember. And then once you attach them, it becomes disaccharide and polysaccharides. You're going to see this thing actually in amino acids as well, in proteins as well. We're going to have amino acids, and once you connect amino acids, you're going to get actually proteins. But lipids are not going to be like that actually. So these are, again, as some of them are really, like a very big and gigantic molecule, but they are not going to be like polymers, right? We are not going to be really attaching them. So that's the only difference. Okay. So usually, if you look at the lipids, right, they are insoluble in water, okay? And so they don't really like water because they are non-polar most of the time. And they are soluble in like more like organic solvents such as ethanol, acetone, and things like that, okay? And again, we're gonna learn about other important things. So here is actually the list of the lipids. And actually, this is kind of like a nice table. And in the PowerPoint, actually, it's a little bit, it's not really going with this order, but I'm going to be actually following this order in my, whiteboard. So we can actually categorize the lipids in two different ways. Okay. The first one is the lipids that contain fatty acids. And so we don't know what the fatty acid now, right? But we're going to learn. So if you look at all these lipids, they're going to have fatty acids. Okay. And then we're going to have lipids that doesn't really have any fatty acid. And these are the two of them. Okay? So I'm going to go with this same, description here. So maybe I can go ahead and show my whiteboard now. And you can see it, right? Okay. So again, these are from other section. Somehow I am still having it. So what again? This is the list that I have in the PowerPoint. Okay. Oh, they changed it. They put it here. I like to actually put it. I like to put this on the sidebar. This was actually on the side, right? Again, I changed my laptop during this week. Toolbar location. Let's put this in the left here. Okay, good. All right, so we learned, right? Now, again, there are a lot of things here, but you can just focus on here, right? And again, I was just telling that I'm going to be actually going with this order, okay? So we are going to learn about the lipids, and let's learn about the fats first. Okay, so what are the fats? Okay, so the fats are, right, once you have, right, and if I ask you to look at this molecule right here, what is this molecule? What functional group do you see here? Can you tell me? Does anybody can tell me? What functional group here? What do you see there? Anyone? Guys, you're gonna have a last quiz about this. And what was this functional group, everyone?
That alcohol.
Close, but again, you have a carbonyl here, right? There's a carbonyl here, and if you have a carbonyl attached to an hydroxide, this is my carboxylic acid, right? Carboxylic acid. So now, as you can see here, we have a carboxylic acid. The only differences here is, as you can see, look at the backbone, right? The carbon have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? Usually it's like larger than 10 carbon, right? It's larger than 10 carbon. So if you have such an acid, you're gonna call you a fatty acid. Why fatty acid? Because you are fat, right? Because you have a lot of carbon. It's not just like 2 carbon or 3 carbon. Make sense? That's why we're gonna call you fatty acids. And then on the other hand, if you look at the red molecule here, this is actually, as you can see, this is glycerol, right? And again, you don't know the structure of it, but the only thing that you can tell me here is, as Marco said, this is a polyalcohol, right? We have high OH here, OH here, OH here, okay? And again, the name of this guy is glycerol or glycerin. And you can actually find this at the market, right? In the marketplace, you can buy it. And there is nothing dangerous about it, right? You can actually even eat it. It has a sweet color, sweet taste. And so it's available, commercially available everywhere, okay? So again, once you kind of like mix these two, then we are gonna get actually, again, if you mix them together, right? If you mix them together, as you can see, this is actually $1 million question. Let's see who is gonna answer. If you have alcohol, and if you have carboxylic acid that I just draw here, does anyone remember what we get after we mix these two? What functional group were we getting? Anybody remember? Remember, you were losing water here, right? And then we were getting something here. What was that? What functional group was that?
A ketone?
Nope.
You're in the right after ketones. What's right after ketones?
So we have a we have a carbonyl attached to an oxygen and another R. It was esters, right? Esters.
Yeah, there you go.
Okay, so it's gonna be esters basically, right? So if you mix them together, right? So if you have a glycerol and if you react it with fatty acids, then it's gonna be the same thing, right? You're gonna be actually making a bond between these two guys. So this guy is gonna attach direct to, maybe I can show you like that, to this carbonyl, right? Right there. See? As you can see, this is nothing but an ester, right? You have a carbonyl attached to an oxygen, and oxygen is attached to an R group. It's just like this guy. O and R. You see that, right? And same thing here, because you have 3 of them, right? You're going to have 3 of them like that. Okay? And same thing here. You see that, right?
Yeah, I see it.
Yep, very good. And again, so once you have glycerol mixed with the fatty acid, then we are going to call you fats, okay? Or we are going to also call you triglycerides, okay? So these are the same name, but in reality, triglyceride is more like a technical name, I guess, but fats are more like a public name, but it is these fats that we are talking about, okay? Make sense? So again, and this is going to be our first lipid, and this is going to be our fats. And as you can see, depending on, there are a couple things that I want to talk about here in fats, right? You can actually have different fats, correct? You can have, if you look at these fats, do you have any double bonds in this fat?
Yes.
Where is it?
It's with the oxygen.
Yep, it's right here, right? So
Yeah.
do you see any double bond in the fatty acid part on this carbon chain?
No, there's no double bond. It's just the first carbon.
Yep, there is no double bond, right? So again, because there is no double bond here, we're gonna call this a saturated fat, right? Because there is no double bond on my carbon back chain. Make sense? That's why it's gonna call saturated fat, right? So if you can think about it, right, you can actually have double bonds here, right? Depending on the fatty acid that you have. Again, whatever you can have, you can actually mix up, and then, you know, again, this is organic chemistry, right? That's the beauty of organic chemistry. So depending on the structure, right, you can actually introduce a double bond here, like that. Make sense? All right. So therefore, if you have a double bond, what do we call you?
Unsaturated.
Unsaturated. Very good. Okay, so this is going to be unsaturated if you have a double bond. Okay, and it turns out that if you have a double bond in the fatty acids, okay, then you're going to have, it's going to have a very, effect on the structure of the molecule. Okay, and as you can see here, okay, again, we didn't cover this in organic chemistry whenever we are doing the alkenes, because again, we don't have that many of time. But as you can see, this double bond can be oriented in two different ways, okay? So as you can see, this is the first way, right? And if you look at the hydrogens here, right? If I count the carbons, we have 1, 2, 3, 4, then there is hydrogen here, 1, 2, 3, 4, and there is hydrogen here. You see that, right?
Mm-hmm.
So as you can see, the hydrogens are in the opposite direction. You see that, right? It's clear, correct?
Yes.
Okay, very good. Okay. And so these are, again, called unsaturated fats. We are talking about unsaturated fats. And so these are going to be, again, in organic chemistry, right? Let me actually, again, you don't have to know this. Okay, you're not going to be responsible. But we talk about stereoisomers, correct? And as you can see, these molecules, there's a nice bird sound coming from.
That's my neighbor's got
All kinds of birds in the backyard.
Oh, nice. Okay, so hydrogen and hydrogen, there's a double bond there, right? And then hydrogen and hydrogen. Do you think these two molecules are going to be the same molecule or different molecule?
They look like they're going to be different because the hydrogen's in two different locations.
Right, two different locations. And again, if you have a double bond, right, you cannot rotate it because you cannot break up the double bond. Okay, again, I don't have the molecules right now with me, but again, we didn't really cover this in the alkene, but you know, in organic chemistry, if you take organic chemistry, if you like it, we're going to call this, again, these are two different molecules, even though they have the same molecular formula. And the connection, right? We talk about the connectivity of the atoms. Connectivity is the same, but as you can see, the orientations of the hydrogens are different. And therefore, we're going to call this a trans isomer, and we're going to call this a cis isomer. Okay? So as you can see, if you look at these hydrogens, right, they are on the opposite direction. You see that, right?
Yeah.
So therefore, this is going to be called what isomer? Trans.
Trans.
Right? This is actually where we said, so this is going to be my trans fat. You probably heard about this, right?
Yeah.
Trans fat, right? If you heard about it, there are a lot of like hype about it. And again, these are not hype. And it turns out that these trans fats are the one that's actually causing all the, what do you call that? You know, it kind of like clogs your vein in your blood cells and things like that. And this is the responsible fat. And this is called trans fat. And the reason is, again, because as you can see, the structure, let me show you. I don't have, yeah, I can actually maybe show you right there. Okay, so this will be my trans, right? And let me draw you the cis somewhere here. And then you will see a big differences, right? So I'm just going to show you this part, okay? So you're coming here again, right? There's our group here. You're coming here, here, and here. And then you're going to need a cis double bond. So in order to have a cis double bond, right, the hydrogen has to be on the same side, like that. And then you have to put this this whole kind of like group on the other side. You see that, right?
Mm-hmm.
Like that. Make sense? Something like that, right? And then there's it's attached to again, there's a carbonyl here and oxygen here and whatever, right? So I'm not going to draw a whole thing, but you got the idea, correct? Right? So now again, you have this molecule and this molecule. So if I ask you, which one do you think is going to be easy to pack? Let's say you are packing this molecule and you made it on your table, and then you want to pack them together. Which one do you think is going to be easy to pack?
The trans fat.
The trans fat, right?
Yeah.
Why? Because it's more like a straight chain, right?
Yeah.
Yes, Carlos, you're right. And so therefore, again, if you have a trans fat, that's one of the reasons it'll be easy to pack. And so therefore, usually the trans fat are going to be solids, right? And so whenever you eat them or whatever, right, it's going to be solids, and that's why it's going to be clogging your veins most of the time, okay? But as you can see, if you have a cis fat, again, not trans fat, and this is actually, I can give you one of the examples, like oleic acid, for instance, oleic acid. What's oleic acid? Anyone know? This is olive oil, right? And olive oil, this olive oil is it solid or is it liquid at room temperature? Obviously, it is liquid, right? Because you put it on your salads, right, and things like that. Again, I love olive oil, and you can do a lot of things, right? And again, this is one of the reasons why olive oil and oleic acid is liquid, because the molecule, we call this actually a kink, right? They have a kink in their structure, kind of like a, going in a different direction. And imagine this one is also kink, and this one is also kink, and this one is also kink, right? So it's like 3 kinks in the structure. You know what I mean?
Mm.
Right? So it's going to be very, very difficult to pack this molecule. And if it's going to be difficult to pack, then the melting point is going to actually get lower and lower. But if it's easy to pack, the melting point is going to get higher, as we've seen in the trans fat. Make sense?
Mm-hmm.
Okay. So again, these are 2 different isomers, trans and cis. And whenever you have a trans, we call them a trans fat. And that's why it's called trans fat. All right. Do you have any question with this, anyone? All right, cool. So now I want to talk about one more thing or a couple more things here in the fast, and we can move on. We have, as you can see, I didn't lead this rancidity because I forgot talking about it. These are, what is this rancidity and iodine number? So let's talk about the rancidity. Rancidity here is, again, if you have fats, right? Then, depending on, again, if you have, if you have a double bond here, or even if you don't have a double bond, right? If you keep this fat outside, right? Usually, if you have a lipid, if you have a, like if you have butter, for instance, where do we keep the butter? We keep the butter inside the refrigerator, right? Yeah. And why? Because if it gets hot, and then because you have a long chain, okay, either because of the heat, right, or because of the sunlight too, right? It can actually absorb the sunlight or heat, and then you might be actually breaking up these bonds like that. Make sense? So instead of, imagine there is a carbon chain of 10, then you're breaking up this bond, and then you're going to be creating new functional groups, okay? And as you can imagine, this will be actually create a problem, right? And this is actually called, again, rancidity, right? And so the rancidity is whenever you are breaking up the fatty acids carbon chain, and then creating like a smaller molecules, right? Like smaller molecules, and then you're going to create some extra molecules. I don't know. I'm just breaking up here, and then you may get like carboxylic acid here and there. You know what I mean? And this will actually, again, affect the quality basically of the fatty acid. And this is one of the reasons actually, if you have butter, for instance, and if you left out the butter at room temperature, right? And I hope you don't have a messy, kitchen, but and then you start smelling. Even in the refrigerator, if you keep the butter so long, right, it's gonna start smelling. Okay, and so what are those smells are coming from? Those are the smells coming from because of these small molecules. Make sense? You're creating something that's not really good, and obviously not as healthy as butter itself. Make sense? And that's going to be called again rancidity. Okay.
So rancidity is a breakdown of fats.
Exactly, breakdown of the fats. Very good. Very good. Okay, so once the fats break down, then you're going to get rancidity. And then we have this iodine number, and again, this is useful especially for comparing the unsaturated either fats, right? Either cis or trans, doesn't matter. As long as you have unsaturated fat, as long as you have a double bond, that right? How we can compare how much unsaturated, right? I want to know this unsaturation number. Okay, so what do? I add iodine to this solution. Okay. And I think we did this in the lab. I wasn't really sure. On ground lab we are doing this lab, but I think in the remote we didn't have this. So you can actually add this iodine to any double bond, and this is actually how you can detect the double bond. Iodine is going to add to the double bond, and iodine is a reddish color, brownish reddish color. And as soon as if you have an alkene, and if alkene is present, then iodine is going to add it to this double bond, and it's going to lose its color, right? This is going to be colorless. And then you will say, okay, boom, you have alkene. Okay, so as you can see, we can measure how much iodine that we are adding, right? Let's say you have 1 gram of unsaturated fat, and then you get some sort of like a number. Okay, so this is what we call iodine number. So as you can imagine, if it's the higher the iodine number, then you're going to have a higher unsaturation, right? Make sense?
So it works like almost similar to what pH is. So the higher the number, the more base it is. So the higher the number with iodine, it becomes more unsaturated.
Yeah. I mean, but I will be like, comparing with the pH actually. That wouldn't be a good analogy, Carlos. But again, it's just how much you're adding, right? Higher the iodine number, it makes sense, because imagine if you have a 1 double bond here, right? You will be adding 1 mole of iodine, right? You need 1 mole or 2 mole. But as you can imagine, if you have more double bond, right? You need to add this iodine to every single one of them. So you need to add more iodine. Make sense?
Mm-hmm.
Okay. So that makes sense. Okay. All right. And then I have one more term here. It's called again, this is just a technical term, prostaglandin. Again, I think I can show you this in my slides. And so the prostaglandin is, there is this fatty acids here, right? And in the fatty acids, somewhere around here, right? Somewhere around here, again, you don't have to know what it is, but in the fatty acids, right? This is your fatty acids, and we have this actually in our body, and you can actually read it in your books too. Somewhere around here, we have a 5-member ring cyclic, 5-member ring, like 5-member ring. So it's going to be 1. It's going to be, the way that I draw is going to be a little difficult, but you will understand hopefully. So it's going to be like that, right? So 1, 2, you have a 5-member ring, cyclic ring. 1, 2, 3, 4, 5. You see that, right? Somewhere, again, this is the organic chemistry, and you can have this structure because, as you can see, this carbon has 1, 2, 3, 4. There's 1 hydrogen there, 1 hydrogen there. You can have this structure. That's totally fine. Okay, as long as the carbon is happy, right? Excuse me, it has 4 bonds, then you can have it. So this is called prostaglandin. And in our body, there is a very important fatty acid, I believe. Hopefully, I think I have it in the slides. I can show it to you guys. But this is called prostaglandin. Okay? All right, very good. Any question, everyone? All right, so let's move on to waxes. What are waxes? So now we are in the second category, and the waxes are nothing but very simple, right? You're gonna have, again, it's the same question that I asked you earlier, right? You have a higher molecular weight alcohol, right? Again, this is a higher molecular weight, meaning that you're gonna have a carbon chain, again, larger than 10 carbon, very high. And then if you have mixed this with a fatty acids, right? You're just gonna bring one fatty acid because you have only one, again, alcohol here. What do you think you're gonna get? If you mixed alcohol with carboxylic acid, what do you get? What functional group you get? What was it again? Esters, right? Again, I don't know who said that, but so it's gonna get, you're gonna get an ester, as you can see, okay? And as you can see, once you mix them too, you're gonna get a wax. This is what we call them, a wax, okay? All right. And the only difference is here though, if you look at the waxes, the wax has no nutritional values, okay? So it doesn't have any nutritional values, okay? No nutritional values, meaning that, right, you can burn the fats to in order to get some energy, right? Our body doesn't burn the fat right away, right? We burn the carbohydrate first, and if you don't have a carbohydrates, then you can burn the fat. But when it comes to waxes, right, we have the waxes, we have ear wax, and we have kind of like a bee wax, all those waxes you can imagine. This is how you make it. And as you can see, we don't really eat waxes, right? Because it doesn't have any nutritional values, okay? It's not gonna give us anything basically, right? Okay, I'm moving on now. So now things are getting a little bit, interesting, okay? Not so much, but a little bit interesting. Okay, so whenever I have the fatty acids, right? Whenever I have the triglyceride, remember, this was glycerol mixing with the fatty acid. What do I get? I get fat, right? And I said that this is gonna be my triglyceride. So now I'm gonna show you what's mono and diglyceride. Okay, so if you can imagine, if you have only, right, this is triglyceride, as you can see. What do you think the diglyceride is gonna look like? Anyone? Anyone wants to take a guess?
Di is 2.
Di is 2, okay. Which one do you think you're gonna have 2 here then? You can't have 2 glycerol, right? But you can have 2 fatty acid, right? Can't you?
Yeah.
Right? Yes, that's a good guess. So instead of 3 fatty acids, if you have only, see, I'm gonna eliminate one of them, right? And I'm gonna have just the OH here. So as you can see, I'm just having 2 of them. Do you have a question? Someone has a question? Or just a noise? Okay, so as you can see, I have 2 fatty acids. Then because you have 2 fatty acids, now this is gonna become a diglyceride. Make sense? Right? Everybody? Not so bad, right? Right? Okay, so what about monoglyceride? What do you think in monoglyceride is gonna look like? Anyone? If this is diglyceride, what do you think the monoglyceride is gonna look like?
It's going to be 1. It's
One,
gonna be
exactly.
One
Exactly.
OH.
Exactly. No, not one OH, like two OH, right? You're just gonna get one fatty acid. If you have 1 fatty acid, then it's gonna be monoglyceride. If you have 2, it's gonna be diglyceride. Okay, like that. Okay. Make sense?
Yeah.
Okay. And you can actually see this mono and diglycerides. I can guarantee you, if you go to any market right now and if you buy any food, right, any like cookies or any, I don't know, like ice cream or you name it, right? You will see this mono and diglycerides like all the time, and I believe again they are adding this to increase the shelf life of the foods, right? It kind of like gives the freshness, even though you keep it long time, right? I mean, like we make bread at home all the time, not all the time, but time to time. And obviously we don't add anything else, right? We don't add like monoglyceride, we don't add, we just have water, you know, flour, and that's it. And whatever you make at home, right, if you just keep it 1-2 days, you will see that it's gonna get like very, very hard. And it's gonna be difficult to eat because you don't add any preservative such as monoglyceride, because these are, it kind of like keeps the, you know, the thing that you're making, again, it can be anything, keeps it fresh. And you can just, you know, keep it like 2 years and then you can serve it to your guests and they're gonna enjoy it, okay? Obviously not 2 years, but again, that's the purpose. All right. So now again, we kind of like did this 3. Now let's move on to our another interesting lipids, and these are going to called phospholipids. Phospholipids, and then you will see 4 different one of them. And again, they have a very kind of like a scary name, like lecithin, cephalin, sphingomyelin, glycolipids, right? But as you will see, they are not as scary as you think so. Okay, that is nothing but a similar fat. So let's move on to our first one, which is lecithin. So lecithin is, again, we are going to have the same backbone, right? So the glycerol is still there, or glycerin. This is my backbone, okay? And then we have this fatty acid, as you can see. This is my first fatty acid, right, on top. And the black one is my second fatty acid, black color. And then again, why we call this phospholipids? Because we have actually a phosphate. You can remember the phosphate was a polyatomic anion, right? Like how I call you this? This is going to be called sodium phosphate, right? This is like, if you have sodium phosphate, again, this is going to be 3 here, right? This is sodium phosphate. This is the phosphate group that we have. And again, the phosphate is, you can see this phosphate group in almost all biological molecules. And again, if I want to draw the Lewis structure, it's going to be somewhere like that. So we have a dog, I guess, watching the lecture. That's good. Okay. And again, you don't have to really know this, but I'm just like showing you to what it is, really. Okay. So as you can imagine, you can add this phosphate group here. You can insert it. Okay. And if you have a phosphate group, then this is going to be, again, is everything all right, everyone? Phosphate, right? So you must have this phosphate group here. Then you are going to be a phospholipids. Why? Because you have a phosphate. Make sense? As you can see in the fats, in monoglycerides, waxes, and fats, we don't have any phosphate. Makes sense, right? And then you're going to have this group here, which is going to call, let's say, X. And if you change this group, then you're going to have a different phosphates. Okay. So the first one here is, if you have phosphate and if you add this phosphate to a choline, okay, the molecule is choline. Again, you can just, name the, I can give you the structure of the choline, but it doesn't really necessary, okay? So you might be asking, like, what is the choline? The choline is actually I will just say a nitrogen containing compounds, okay? And such as, again, you don't need to know the structure, okay? I don't think it's going to be really informative for you in this case. So this is, again, called a nitrogen containing compounds. Like you have some sort of like a compound which has a nitrogen in it, like that. Make sense? Okay. Again, the molecule is called choline. Right, in the PowerPoints, I believe I have the structure. I can show you there. All right, so this is going to be, again, called what are we going to call this? This is going to call lecithin. Okay, if you have this whole structure, right? If you have glycerol, 2 fatty acids, and then the phosphate in the third one, you don't have a fatty acid, but you have phosphate attached to a choline, then we are going to call you a lecithin. Okay, makes sense? And as you can see in the notes here, I'm saying that we are using, right, in our body and in the industry as well, we are using this as, it is a very functional group. we are using this as emulsifying reagent. I written here actually. Let's just circle that. This is called an emulsifying agent. Does anybody know what emulsifying means?
Yeah, it's just like what an Alka-Seltzer does in water. It bubbles up.
Yeah, I mean, kind of, yeah, right? And,
Yeah.
Yeah, so emulsifying agent is, again, if you look at this, we said that the lipids are not soluble in waters, right? So these are not soluble in waters. So if you have, again, I kind of like try to draw in here. Let me draw it here in a better way. So imagine you have a lipid, and in our body, we consist of what? Water, right? And so imagine you have these lipids, okay? And let's say this is water. So do you think it's going to be soluble in water? No, right? So the lipid molecule are going to be like, it's going to precipitate it out on the bottom of the solution, right? Make sense? And this is all water, right? This is all water. So let's say in our body, we have a lipid here, right, somewhere, and like fat, and we want to move this fat to somewhere else, to another cell maybe, right, by using the blood stream, right? So how we are going to be moving this, right? Because these are not soluble in water. As you can see, once you are, once you have it, it's going to just stay there. As you can see, it's going to stuck there, right? You won't be able to like dissolve this in water, and so that you can move from one location to another location in our body. Make sense? Or even if you have, let's say you get a kind of like a, you know, chocolate milk, right? And if you get a chocolate milk, you know, like in this bottle, for instance, whenever you go to like markets, I know nowadays they are kind of like hiding the bottle, right? You don't really see what's inside, but imagine if you don't use any emulsifying agent, all the things, because those, you know, those things, we call them emulsion, right? Emulsion, what emulsion is? Emulsion, it's not 100% dissolved, right? So you will see them in the on the bottom of the bottle. Okay, if you don't use any emulsifying agent. So what the emulsifying agent does is it somehow, you know, helps these particles, right? Like fatty, you know, oily substance. It helps to hold in a suspension, right? So they are still not dissolved, but instead of like staying on the bottom, they are kind of like hanging in there in the water like that molecule. Make sense? Like that, right? This is what the emulsifying agent does. Instead of like sitting on the bottom, right? Otherwise, you will see that they are sitting on the bottom, and you won't be able to like move them around and again, you know, use in a way that you want. So emulsifying agent makes you know, hold those particles in suspension, basically. Suspension. Make sense? And again, this is how you can transfer one lipid to another, you know, one lipid from one location to another location. Or again, in industry, right, if you're making a drink, for instance, like a chocolate milk, right, you need to add some emulsifying agent. And again, if you read the descriptions of ingredients, you will see they're going to say emulsifying agent, emulsifying agent. And what is it? It's lecithin, basically. Okay. Make sense, everybody?
Yep.
Okay, and you can also find this lecithin in, I forgot to tell you, in egg yolk as well.
Yes.
Okay.
The white part, not the yolk itself.
Yes, I believe so.
Yeah, the white.
Mm-hmm. All right. Any question with anyone? Okay, good. So now, again, we've done the lecithin. Okay, what about the cephalin?
Sounds like a veritable disease.
Okay, we're done with the lecithin. So let's move on to cephalin. And again, cephalin is, it's the same thing, okay? All right, cephalin here is, as you can see, I had a drawing. It's gonna save us some time, right? The backbone is still the same. You see, this is my backbone, right? This is my backbone, you see that? And again, I didn't draw the whole thing, but you still have glycerol, okay? And then you're going to still have 2 fatty acids here. These are my 2 fatty acids. Let's write it down. And then you're going to obviously have phosphate, right? Otherwise, we're not going to call you phospholipids. And so instead of a choline, right, you're not going to have choline, but you're going to have something else. And this is actually, you can have like ethanolamine, like this molecule, for instance. Ethanolamine is, as you can see, this is 1 and 2 carbon. And if you have 1 and 2 carbon, we are going to call ethanol. And this is an interesting molecule because, as you can see, we have a functional group, 2 functional groups at the same time. Right? This is my ethanol. And this is my amine. Right? This was the amine part. Again, I draw very poorly here for some reason, but my drawing is not always good. Okay, so this is amine. You see that, right? NH. Like if you have a hydrogen, we call you amine, unless you are connected to a double bond carbon. But here there is no carbonyl, so we are going to call this ethanolamine. Okay, so it can be ethanolamine. It can be again a serine. Again, I'm not going to give you the molecules, and it can be actually the another one is, I believe it's anositol, something like that. But again, the key here is, right, you're not going to have choline, basically, right? If you don't have a choline, as you can see, no choline, right? If you don't have a no choline, then we are going to call you a cephalin. Make sense? Okay. And then you might be asking, like where the, like where do we use this cephalin? What's the important function? And again, because of this molecule here, as you can see, as I drawn here, right? We are using this actually in order to, involve the blood clotting, basically, right? If you have a, let's say, if you have a cut or something, right? It kind of like helps you to clot the blood, basically. Okay. That's the function of the cephalin. Any question, everyone? Everyone's good? All right. So now, again, we're done with the lecithin and cephalin. And now this is the last 2 in this category, as you can see. And in these last 2, we're going to change the backbone. That's the only thing. Change the backbone. What I mean by that is, as you can imagine, in the lecithin and cephalin, what backbone did we use? We use glycerin or glycerin, right? Or glycerol. So in the cephalin, in the sphingomyelin, we are changing the backbone, as you can see, right? So this is my sphingomyelins right here in the middle, as you can see, okay? So as you can see, instead of a glycerol, now we are using a different backbone. What is that backbone? We're going to call sphingosine, right? Sphingosine is, as you can see, this is the backbone we are using, like carbon, oxygen, carbon NH2, and then carbon, oxygen. And obviously there are a lot of group here. Like again, I didn't draw here, but there's a lot of group here. But this is the main functional group here, as you can see. As you can see, this is not glycerin anymore, right? In the glycerin, we have 3 hydrogen, 3 OH attached to like that. But in the sphingosine, we have an amine here, like that. And there is an R group here, like a huge R group. Again, we are not drawing, but you can get the idea. Okay. So this is again sphingosine backbone. So in the sphingosine again, we are using this backbone. And so in the first one, I'm attaching my fatty acid without a problem. And amine is staying as it is. And the third one, on the second one, sorry, just like the lecithin, I have my phosphate group again, right? Attached to a choline. Remember the choline, my friend choline, right? And then if you have this structure, then we are going to call you a sphingomyelin. Okay. Yeah, does this make sense, everyone? And the sphingomyelins is, I believe actually it's used in our nerve cells. Okay, I think I have somewhere here in my notes. Yeah, you can actually, yeah, you can, you know, sphingomyelins in our brains, you know, it has a lot of functionalities, but again, you're not going to get into those details. All right, any question with this, everyone? Everybody's good? Okay, so now what about the glycolipids? And again, glycolipids, the name is kind of like telling you, right? Glyco. So what's glyco is, again, you're gonna still have your sphingosine. The backbone is still different, as you can see. It's not glycerol, right? This is sphingosine. And then you're gonna have your fatty acids in the first one. You're gonna have NH2. And the last one, you're gonna have this OH is gonna attach to a galactose. Remember, the galactose, our old friend, right? Galactose was, again, it was a monosaccharide. And imagine there's a 6-member ring, right? Again, this is, we're not gonna draw the galactose, but it's somewhere, it's attached to a carbon, right? And you're gonna have actually a chain structure like that, if you can remember. We don't really get into, right? It's gonna be like galactose, somewhere like that. There's gonna be, again, a lot of OHs here, there, right? And this is gonna be attached to here, basically like that. Make sense? Again, this is like a huge molecule, a little bit large molecule, but that is what it is, okay?
Is that galactose?
A double bonded?
Nope, it's actually, it's, you weren't here last time, Carlos, right? We've
Yeah.
seen this, right? Galactose is, again, it's a 6-member ring like that. But in real life, it has a chain conformation, and there are a lot of OHs here, right? Because if you have a 6 carbon, you're gonna have 6 water molecules, right? And that was the structure, and you're gonna have 6 OHs. Again, I don't know where this OH is exactly, right? There's OO and there's CH2OH, somewhere like that. But again, you're attaching this molecule to here, basically, right? That's what it is.
Okay.
Okay, you don't need to know the structure of the galactose. I'm just
Right.
okay. All right, everyone. Any question with this? Everybody's happy? Right? So again, this wasn't so bad. Let's summarize again. Let's summarize again here. Let's go back to my first table here. Now again, right, what was the fats? The fat was, right, you're gonna have glycerol, right? You have a glycerol and then fatty acids, okay? If you mix the glycerol with fatty acids, then you're gonna get fats. Wax was, you're gonna have very heavy weight alcohol, like a long chain alcohol, mixing with the fatty acids. And then we've seen the mono and diglycerides, which 1 or 2 fatty acids, right? And then the phospholipids, you need to have a phosphate, but here, right, in fats, waxes, monodiglyceride, phospholipid, lecithin, and cephalin, we use a backbone of glycerol here, right? Glycerol backbone. So only sphingomyelin and only last 2, we are changing the backbone. So in the phospholipids, we said that, you know, if you change the one of the fatty acids to phosphate and choline, then you're going to get actually lecithin. And if you don't have any choline in the last part, you have cephalin. And finally, if you change the backbone to, again, sphingosine here, you can either have a sphingomyelin or you can have a glycolipids, right? All right, very good. So let's go back here and cover the last 2 here. But I think I'm going to cover the last 2 from our slides. Let me see if I have anything missing here. Let me zoom out. Wow. Nice and neat, huh? See, you can have a large whiteboard. Okay. Any question, everyone? All right, so now let's go back to our PowerPoints. And again, I'm gonna move a little fast here because we already covered all this. So there are some more information about this. So maybe if I need to, I can go over a little bit, but then I'm gonna move to the last part of the slides, okay? So again, these are all definitions that we've seen. So let's try to identify each one of them. Let's do some exercise. So which one do you think the first one is? A, you have a fatty acids, you have a sphingosine, and you have a carbohydrate. What am I?
You are a single gold malin, however you pronounce that.
What, say it again.
Sphingomyelin.
Sphingomyelin.
Yeah.
You are okay, sphingomyelin, but which one? Which one?
Oh, which one? That will be the glycolipids.
Yes, glycolipids, right? Why? Because you have again a carbohydrate, and if you have a carbohydrate, then you're going to be called glycolipids, right?
Right. Mm-hmm.
Everyone is good, right? This will be glyco. Hopefully, I'm spelling the right way. Glycolipids. Makes sense, right, everyone? I'm hearing only Carlos' voice, but I think Carlos is our, you know, what do you call that?
I'm the
Representative.
spokesperson.
Right? Spokesperson, yeah. Spokesperson, there you go. How come I don't see you guys? I mean, my video is, where is my video? Interesting. Let me. Yeah, I used to see you guys. Anyway, just. Interesting. Yeah. Anyway, all right. So what about the second one? B, you have fatty acid and glycerol. Where are you?
A lipid.
Okay, what I know you're a lipid because we are talking about lipid.
You're a trans fat.
Not necessarily trans fat, but you're fat, right? Fatty acid and glycerol. Again, because we don't know what kind of like fatty acid. Maybe it's trans, maybe cis. We don't know, but at the end of the day, you are fat, right?
Yeah.
You're fat, or we can also call you triglyceride too.
Yes.
Same thing, right?
Yep.
Triglyceride.
Yeah.
Okay.
And fatty acids.
Okay. And a multicyclic ring structure.
That is the prostaglandin.
Yes, prostaglandin. Yep.
Yeah.
Very good. All right.
Huh.
Well, actually, multicyclic ring system is, we're going to actually cover this. Actually, we haven't covered that yet. Okay, so let's skip this question for now. Again, this is another type of lipids, actually, not the prostaglandin, Carlos.
Mm-hmm.
All right. And again, these are some other molecules that we've seen, right? The same thing that I show you. This was my fatty acid, as you can see. Look at the fatty acid. How many carbon do you have? This is, again, a palmitic acid. And again, these acids, you will see in all of the, like cleaning products and things like that, right? They use this, right? And look at the carbon, 15 carbon, right? As you can see, if you mix them up with the glycerol, then you're going to get tripalmitin, another fat. And again, we talk about this. This is how the general formula is. And again, right, you can actually have different number of double bonds. As you can see, saturated fat 0. But if you increase the number of double bonds, you're going to obviously get different acids. Okay, linoleic acid, arachidonic acid, and these acids are actually very essential acids, by the way. And how can you find where you can find this? Again, if you have 4 carbon fatty acids, it's going to be in milk fat. If it's 6 carbon, we will find it in butter, coconut oil, palm oil, etc. If it's 12, lauric acid, 14, nutmeg oil, And as you can see, 16 and 18, you're gonna see this in animal fats, the real fat that we're talking about actually, in meats and things like that. And look at this, peanut oil, and it has actually 20 carbon, and this is called Parahedic acid.
Professor, didn't they make soap out of animal fat?
Yes, they do, and I'm going to show you that actually how you can make it in the slides
Okay.
soon. In my organic chemistry classes, we make soap too, and again, these soaps are nice soaps. It's beautiful, smelly, and I use it all the time in the shower and in the bathroom, etc.
Okay.
Okay, so again, these are how it's occurring. We don't have to worry about it. The one thing here is, again, I didn't mention this in the whiteboard, but look at the melting point, right? So as you can imagine, remember, right? How can you increase the melting points, right? If you actually increase the carbon chain, right? If you have a carboxylic acid like that, for instance, right? Which one do you think is going to have a higher melting point? This guy?
The one with the most carbon.
Right, exactly, very good. So if you increase the carbon chain, right, then it's going to get fat. It's going to get higher and higher, and it's going to be easy to pack this molecule too, and this will have a higher melting point, correct?
Mm.
Okay, very good. And what about let's look at these ones, and these ones, I believe, it may have a same carbon or not, but as you can see, we are increasing the number of double bonds. You see that, right?
Yeah.
And as you can increase the number of double bonds, then especially if you have a cis double bond, right? Imagine if you have a cis double bond, then you're going to have a kick like that, right? Like that, right? So this is trans, right? Sorry, this is cis. Then it will be difficult to pack. And as you increase the number of double bonds, as you can see, it's going to be even much harder to pack. And as a result, melting point is, as you can see, it's decreasing. You see that, right?
Yeah.
Okay, and that's the reason why the melting point is decreasing, because you are increasing the number of double bonds, and that's going to cause a problem to pack the molecule basically. Okay, so for instance, this one, for each of the fatty acids, state whether it's saturated or unsaturated. If it's unsaturated, decide whether it's the number of oleic. We don't have to really know. But as you can see, this one is actually saturated, right? There's no double bond. This is saturated. And this is unsaturated. You have a double bond right here, right?
Yeah.
And as you can see, this is also unsaturated. You have a double bond there and double bond there. Okay? Make sense? All right. Again, you don't have to worry about the other two, because you have to really memorize this. But I don't even know, to be honest with you, right? I don't want you to memorize things. I want you to understand the reason behind it. All right, and again, this is another reason why we are going to have, as you can see, this is kind of like telling you, right? If you increase the saturated fats, then you're going to have higher melting point. If you have unsaturated fatty acids, then you're going to have a lower, right? The melting point is going to be lower, because if you have a double bond, as we've seen, and this is one of the reasons why the vegetable oils, right? The vegetable oil, and that's why everybody is hyped about this vegan thing, right? Because it's liquid, and so it's a more healthy, they say. Okay. And again, this is like not so much chemistry, but I think it's a good information, right? There are 3 fatty acids we cannot really synthesize by our body, and these called essential fatty acids, and they are linoleic, and arachidonic acids. All right. And this was the molecule that I was talking about, right? So now, as you can see, I have my fatty acid right here. This is my fatty acid, a lot of carbon.
Mhm.
And as you can see, and this is actually unsaturated. I have a double bond here. You see that? I have a double bond. And in the middle of somewhere, I have a 5-member ring. As you can see, this is actually 5-member ring, but even I have a carbonyl here. So it's a ketone group, right? So it's a cyclopentanone, something like that. So this is called prostaglandin. And as you can see, we can actually find this molecule in our vitamin E too. Okay.
Mm.
And it has, as you can see, it has a lot of functionalities, right? Digestive, cardiovascular, reproductivity, and respiratory functions. And again, you don't need to know the structure of this molecule, but as you can see, once you break this molecule up, once you break the cyclic ring, now this is uncyclized, and this is uricanoleic acid. And again, we use this molecule to synthesize, right? We go from here to there, basically, right? You can close the ring, and you get the prostaglandin. But how you are getting it? You are getting it from this acid. Make sense? You see that, right? Boom, 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 boom. Maybe I can show you like that. I can go back and forward. And then you see there's this 2 carbon. You see that, right?
Yeah.
Okay. So you can synthesize the prostaglandin from arachidonic acid by closing the ring like that. Okay. And again, we've seen this glycerol. You don't have to worry about this. Oh, this is one interesting thing that I forgot to mention. Actually, this is like a very good driver. And you can actually have, if you have a glycerol is a very interesting molecule too. If you actually react with the nitric acid, you can actually synthesize nitroglycerin. Okay. And back in the days, the small amount of nitroglycerin they use as a vacillator, right? Vacillator is what is vacillator, Carlos?
Oh.
To put you asleep, I guess, right?
Of that, it helps with the blood flow. It lowers the. Yeah, that's what that is.
Yeah.
Does something with the blood.
It dilates your vessels.
But yeah, you go.
Yeah.
That's a good
Yeah.
answer.
Yep. But it turns out that actually, if you have a large amount of nitroglycerin, right, this is actually also explosive.
Yeah,
Interesting.
that's what I thought you wanted me to say.
Right. Right. You know about this?
Yes,
Tell me. And again, this is actually, I believe, this is kind of like a liquid, okay, and this is even like very explosive because like if you kind of like because you have this nitro group, right? This nitro group is very unstable, and it will just decompose, and it's going to create a lot of gas, and that's why we call something explosive, Carlos.
Because it detonates and it's heat related. When it starts breaking down, it generates its own heat. And then
also,
and then it's just a breakdown of it's a chemical reaction, to tell you the truth, because it detonates on its own.
Yeah. So again, it's because these are again somehow it's very reactive, and again it's so reactive that even sometimes like if you shake the molecule, right, it's gonna get enough energy to react. Right. If you have, imagine if you have like an age, I know I don't want to make this analogy so bad, but if you have a hyperactive kid in your, in your family, right? Even if you like touch him, he's gonna activate it. Like it's gonna be like like it's gonna be like acting weird. I don't know. You know what I mean? Like it's kind of like that, right? So the molecule sometimes is gonna have higher energy, and the guy actually who invented this is Alfred Nobel. You know, the Nobel Prize that we are getting, actually, he is the guy who invented this. And but he found a way, because whenever they are making this nitroglycerin, even in their factories, they have explosions, right? And he lost, I believe, his brother actually in one of his factories. And then he later on find a way to make it more stable. and then that's how they make those dynamites. You know the dynamites
Yeah.
that we've seen in the cowboys movies, and he was actually putting a kind of like he was molding it in a dynamite, and then he was using a detonator to make an explosion, obviously, and that's how he made billions of dollars by selling dynamites back in the days, because everywhere, you know, we were getting to industrial nations, right? We were like getting, you know, gold, you know, like this and that in every countries, and that's how we got, you know, very rich, and that's when decided to make the Nobel prizes to kind of like, you know, repent, I guess, in a way, you know, because obviously the dynamite was used in the wrong way too, right, to kill innocent people, I guess. And that's why he decided to give Nobel Prizes back in the days. All right. So that's a little bit of triba. And again, these are monoglycerides, right? And diglyceride and triglyceride. And again, the differences here is, as you can see, in the triglyceride, we have 3 fatty acids. In the diglyceride, 2, monoglyceride, only 1. Okay. So I'm not going to go into, and we talk about the iodine number. You don't have to worry about the acrolein test. And remember, like I said, that you can actually make you can make fat, right? And again, this reaction is actually reversible, okay? And so by mixing, again, your fatty acid, this is my fatty acid, right? And this is my glycerol. If you mix them together, you can get fats, right? But and now we are getting to actually Carlos' question about the you know, the soap and things like that. And again, if you have a fat, this is your fat. If you can actually hydrolyze this, hydrolyzing means you're adding water, okay? And then you can actually reverse this reaction back, and you can get your glycerol and your fatty acids, okay? So hydrolyzing means, again, you can do this again in our body. Obviously, we are using this. We are, you know, using enzymes and things like that. But you can do this actually in the lab as well by acidic or basic condition. And again, this is how you can make soaps, right? So once you have your fats, as Carlos was saying, this is your fat. And if you use sodium hydroxide under basic condition, as you can see, you can break up this all bonds, right? And then you will create your glycerol, and then you're going to have your soap molecule. This is nothing but, again, because this is basic condition, right? You're going to have this OH minuses, and because of that, you're going to have a sodium too. And again, this is how the soap molecule is created, because now, if you look at it, this side is going to be non-polar, right? And this side, because of the ionic interaction here, right, you have negative charge here, O minus, and then sodium. So this side is polar. As you can see, this is an interesting molecule because it has 2 different sides. I mean, 2 different, you know, type of polarity in one molecule. And this is great for cleaning purposes, right? Because this side can interact with water, right? So that it's going to be dissolved in water. And this side, on the other hand, the non-polar side, it can interact with the dirt whenever you are washing your dishes. Make sense? So that it can dissolve, right? And then you can get rid of all the dirt. And then once you wash with water, everything is going to be cleansed out. Make sense? That's how it's going to act and do its function, basically. All right? And again, we talk about rancidity, right? And right, when the fats are exposed to air, they undergo 2 reactions, either hydrolysis and or oxidation. This causes them to have poor taste and odor. And again, this is one of the reasons, right? In all the products that we buy from the market, we use antioxidants so that they don't really break up. And vitamin E is actually a natural one, natural antioxidants. And then we're gonna see that. I'm gonna show you the vitamin E in the last part. Again, we talk about waxes, They don't have any nutritional values, right?
Right.
And they are not easily hydrolyzed as fats, okay? And you know what the fats are. Again, these are all information. And now this is phospholipids. Again, you have a phosphate group, right? And then you're going to have an X here. And depending on the X, you can actually have a lecithin, which is a nitrogen containing compound, right? Which is a choline. And we use as emulsifying agent. And then if you change the, the choline to another molecule, which is these molecules, either ethanolamine, serine, or inosol, then you're going to get a cephalin. And then we've seen sphingomyelins. Yes, sphingomyelins, and again, as you can see, we can find this in our brain, in our nervous tissues, okay, where they form part of the protective coating on the nerve, right? We have this nerve cells like that, right? So they are actually protecting our nerve cells, basically, okay? And we have a condition if you have too much of sphingomyelin build up in the brain. That's actually another one. And again, this is glycolipids is seen. And these are some of the informations. And you don't have to worry about these diseases, by the way. I'm not going to be asking. Okay. So now, again, I'm done with the fats. The lipids that contains fats, right? But we are going to have, as you can see, lipids, right? If you can go back to my table again, we're going to see these are going to be, again, lipids that doesn't have fats, right? So these are no fat. But we're going to be still call them and classify them as lipids. And the first one is steroids. Okay, so what are the steroids? Steroids are organic molecule based on a interlocking 4-ring structure. So as you can see, we have 1, 2, 3, 4 structure, and then we've seen this, right? This is like cyclohexane, right? We have cyclohexane here, another cyclohexane here, another cyclohexane here, and cyclopentane here, right? So once you interlock them, then we are going to call you a steroid, okay? This is how the general structure of the steroid is going to look like. And steroids are going to be, again, very important functions in our body. And if I can give you one of the example, like the hormone, the testosterone in a male hormone, as you can see, it is a steroid. We have 1, 2, 3, 4 interlocking system. So these systems obviously have different functional groups, right? What is the functional group here? What functional group is this? Anyone?
Wow.
What was this? Anybody remember?
That is.
Amy, Bianca, let's hear from someone else. Christine, Jessica, Manuel, Marcos, Stephanie. We got 2 Stephanie. Thomas.
Is it a ketone?
The ketone, right? Yep, it's a ketone. Very good. So this is a ketone. So again, I might give you the structure and I might ask you to identify functional groups, right? This is a ketone. And now I have an alcohol here too, OH, right? This is an alcohol, right? And then I have an alkene here, obviously, but you get the idea. And again, this is a steroid, and again, this is a hormone in our body. And I'm going to show you an interesting one. This is again a male hormone, and if you look at the female hormone, it's very close. Look at it, right? So it is 4 interlocking system, but instead of a ketone now, you see this is an alcohol now, right? And this is actually a phenol. the specific name is phenol, but you can tell me alcohol is fine. As you can see, by changing from ketone to an alcohol, and as you can see, we have a methyl group here, but no methyl group there, and everything else is the same, right? But once you have that, then you change the molecule and it becomes an estrogen, a female hormone, okay? It's a very important molecule too. And this is another one, again, different functional groups, and it has a different functionalities. As you can see, we kind of like emphasized, right, how similar is the structure. Look at this structure, right?
Yeah.
It's like almost like so close. Like if you compare the testosterone with the second one, the progesterone, right? Look at it. Look at it. Like we have only exception here is this guy here, right? By changing the hydroxide to ketone, as you can see, it changes a lot of things. Okay. And another important steroid is in vitamin D, and this vitamin is necessary for the proper absorption of the calcium from the small intestine. And again, if you look at the vitamin D, you can actually, this looks like a open cyclic system, but you can actually close the system very easily like that, right? You can actually bring this double bond here, and then you can close it. Again, it has like a two form, right? Open form, but you can actually close the ring too, okay? And again, we're gonna call vitamin D is also another steroid. And cholesterol, look at the cholesterol, right? Again, there's a good cholesterol and bad cholesterol, and I'm not an expert to talk about it, but this is another steroid molecule, right? As far as the chemistry is concerned, we're gonna call cholesterol as steroid too. And again, cholesterol plays a role in development of, right? You can actually, it can cause you clotting in your vein, as you can see, right? This is the artery, normal artery, and this is actually completely blocked, as you can see. So the blood is going to be really having a hard time to pass through these walls. And so this is the second type of fats. And again, the first one was steroids, and the second one is again terpenes, okay? And again, terpenes are gonna be, we're gonna call them lipids. And even though they don't have any fat, they're gonna be actually, they're gonna be lipid. So terpenes are the polymers of isopyridine. And again, isopyridine is nothing but, as you can see, there's a double bond here and double bond here, right? If you want to name it, it's going to be 1, 2, 3, 4, right? It's going to be some sort of like a butene, right? And it's going to be actually not butene. We have 2 dienes, so it's going to be butadiene, something like butadiene. Like we have 2 double bond. You don't have to really worry about this. And if you look at the double bond, it's going to be 1 and 3, right? 1, 3. Some sort of like, and then you have substitutions obviously at the methyl position 2. So it's going to be 2-methyl 1,3-butadiene, right? IUPAC naming. But this is again isopyridine, and if you can again, this is my kind of like monomers again, right? If I bring this to another isopyridine, then I'm getting actually a terpene. If I can use structure, look at the carotene molecule, right? The carotene is again, you have a terpene here. So 1 here, 2 here, right? Like that. As you can see, you have a repeating subunit. You see that, right? Like that, somewhere like that, okay? So you're repeating subunit and then you get a terpene. And again, you're going to learn this organic chemistry if you take organic chemistry, but you have a conjugation. Again, we call this as a conjugated molecule, and that's why it's going to have a color, distinct color, okay? Usually carotene is going to have like a reddish orange color, and because it is highly conjugated, it can absorb in the visible light, radiations. And again, vitamin A E, and K are all terpenes. Okay, this is the vitamin A, and I believe, yeah. So I was just gonna say this actually. The vitamin A is a major role in the regeneration of the protein pigment called rhodopsin, found in the retina in eye. So if you look at this, right? I have the slide, but I think I have it in my orgo slide. If you look at this bond here, let's look at this bond here. Right? This is actually a trans, right? Because the hydrogens are on the opposite side. Okay, this is actually how the rhodopsin works. Again, this is vitamin A, and this is attached to some other like enzyme here, right? Like a rhodopsin molecule, like something here. But it actually have this structure. And whenever the light hits this molecule, right, it kind of like this bond absorbs this light and it transfers into a trans molecule like that. Make sense? Again, it doesn't matter, but this is how our eyes is sensing actually. Make sense? So this molecule by absorbing the light, it's actually going kind of like an inter conversion from trans to cis, and then this triggers the mechanism in our eye. It kind of like sends the signals to our brain so that we can actually see. Okay, that's how things are getting triggered basically. As you can see, it's like a small change, right? It's the same molecule, right? And then it can go back to again its trans version after the reaction is done, I guess, right? After it sends the signals, and then so we are doing this like in every second, millisecond in our eyes, basically. Okay, that's how we are able to take out. Again, this is the vitamin A. It's very important for our eyes. And vitamin E, if you look at the vitamin E, again, it prevents oxidation of unsaturated fatty acids, right? And so once you have enough vitamin A, so that your unsaturated fatty acids is not going to get oxidized, so that you're not going to get like those, extra molecules in your system. And finally, vitamin K is aiding the coagulation of the blood once you have an injury, obviously. All right, I think that's the last slide. Oh, yep. Okay, and terpenes and phthalate are known as the fat-soluble vitamins. Yeah, so these are, again, because vitamin A and E and K, right? These are fat-soluble vitamins, meaning that these are not going to be soluble in water, right? So they're not soluble in water, meaning that if you take too much vitamin A, right, then it's not going to be, if you look at your body, our body is 95% of water, 99 maybe, right? So, and if it's soluble in water, then you can actually get rid of it. It's not going to stay in your body, okay? But because they are not soluble in water, right, then if you take too much vitamin, then they're going to be stored in your body, okay? And again, this might cause you a hypervitaminosis, okay? So therefore, you need to be careful about taking these vitamins if you're taking any.
Right.
All right. And I think this is my last slide. And do you have any questions, any concern, everyone?
No.
Let me check. Hold on. I put this.
Well, we're gonna have a final, Professor.
Say it again.
Well, we're gonna have a final.
There's not gonna be final. I think I mentioned this, right?
Yeah, just last chapter is going to be our last test.
Yeah. It's gonna be actually. Let me actually change this first. So today is 17, right? So today is 17. Okay, now it's April 21st. I'm just changing the quiz deadline. For users, and let's save it. Okay. Yeah, so we are not going to have finals again, but I'm going to have one final quiz, but it's going to be just like the regular quizzes. It's going to have the same weight, okay? And that one is going to have the last part of all the organic chemistry, basically, okay? I forgot the chapter name, but all the carbohydrates, lipids, amino acids, and also alkanes, alkynes, and alkenes.
Okay.
Make sense?
Yeah.
But we used to have like a final, but since we are doing this actually remote, since we've been doing this remotely, we are not doing any final. It was a kind of like a departmental final, and everybody was taking the same exam, all other sections, and we were collecting back the finals so that students doesn't keep it. And I think they don't want to change the finals, and they've been doing this every year. And so because this is now remote, you know, we were told to have another final. So instead, we're just gonna have a final quiz, but it's gonna be same weight basically, right? Back in the days, the final was like 40% or something, right? But it's not gonna be like that. Okay, make sense?
Yeah.
And I'm gonna publish the chapter 14 quiz right now, and it's live. Okay, and after this chapter, we have one more chapter, which is amino acids. And after that, we are basically done.
Good.
And so 24th is our last lecture. And I don't think we need to meet again. So I can release the final quiz, and then you can actually finish this up after we've done the amino acids.
Okay.
Okay. I forgot to turn on my cameras, by the way. Okay, any questions, everyone?
No.
Everybody's good?
Yeah, I'm good.